This is the video for section 2.2 on organizing quantitative data. When we talk about organizing quantitative data in tables, we're talking about constructing frequency distributions. This is a little bit more complicated than it was for qualitative data because qualitative data was already organized into categories. Quantitative data isn't, so we have to create the categories ourselves or have the software do it. So what we're going to talk about here is creating the categories or the classes. So the lower class limit of a class is the smallest value within the class, and the upper class limit is the largest value within the class. The distance between consecutive lower class limits or between consecutive upper class limits is called the class width. Here's the frequency distribution for the ages of actresses who won the Best Actress award. So here are our classes, 21 to 30, 31 to 40, and so on. So the lower class limits are just the first numbers in each class. So 21, 31, and so on up to 71. Then the upper class limits are the largest numbers in each class. And notice that here, because our ages are just given in years, we go from 21 to 30, and then the next class starts at 31. Class midpoints we'll use in a later section of this course. And all a class midpoint is, it's the average of the lower class limit and the upper class limit. So all we have to do to find a class midpoint is to add, for a specific class, to add the lower class limit and the upper class limit and divide by 2. So for the first class here, if we add 21 to 30, that gives us 51. If we divide 51 by 2, we get 25.5. So all of these would be our class midpoints. And again, we'll actually use these for something later on. So right now all we're concerned with is just calculating them. Now the class width, this is a little bit easy to get mixed up on. The class width is a difference between two consecutive lower class limits or between two consecutive upper class limits. It is not the difference between the lower class limit and the upper class limit. So to find the class width, you look at two lower class limits that are consecutive, for instance the 21 and the 31, and just find the difference between those two. So the class width is going to be 10, and notice that it's the same no matter which two consecutive lower class limits you look at, or if you look at two consecutive upper class limits, the difference is always 10 here. Now usually we won't construct frequency distributions ourselves, we'll let software do it. If you have a very big set of data, then constructing a frequency distribution by hand is just too time consuming. But we're going to look at how to do it just to give you a little bit more understanding of frequency distributions overall. If we want to construct a frequency distribution, the first step is to divide the range of data values into equal categories. Those are our classes. So this is the most complicated part. Now there are two ways that we can start with this. We can either decide how many classes we want to have, and the number of classes, just to make a frequency distribution that makes sense, should be somewhere between 5 and 20. Less than 5 is too few, more than 20 is just too many. So we can either decide on the number of classes, or we can decide on the class width, whichever one makes more sense with our data. So if we decide on the number of classes first, then we use that to find the class width. The formula for this is that we take the maximum data value minus the minimum data value, and then we divide that by the number of classes we want to have. Once we get that number, we round up to the next whole number. And this is a place that we always have to round up so that we'll get all of our data covered. Once we have found our class width, then we need to find a starting point, or the lower class limit for our first class. This can either be the minimum data value, or it can be a number less than that, if that makes more sense. Now, once we have that initial lower class limit, we find the rest of the lower class limits by adding the class width on. Once we have all of the lower class limits, then we can find our upper class limits. And for these, they have to be less than the lower class limit of the next class. So we can do this by looking at each lower class limit and subtracting 1 unit, depending on how our data is measured. If our data values are measured in tenths, then we'll subtract 1/10. If they're measured in hundredths, then we'll subtract 1/100th, and so on. So once we have all of the class limits, we have our classes all set out, then we just go through our data, and just like we did with qualitative data, we do tallies and we find the frequency for each class. So here's an example of constructing a frequency distribution. So this data represents the time between eruptions for a random sample of 45 eruptions at Old Faithful. And we're going to construct a frequency distribution for this. If we look through here, we can see that the minimum data value is 672 and the maximum data value is 738. So the difference between those two is 66. That gives us an idea of the range of our data. Because at 66, we could go ahead and choose 10 for the class width. That would be an easy one to deal with. And that would give us a reasonable number of classes, because it would give us 7 classes. And again, because our data range is 66, if we divided that by 10, we'd get 6.6, and if we round up, that would give us 7 classes. Next, we need to choose our starting point. We could choose our minimum data value, which is 672, but since our class width is 10, it would be a little bit easier to use 670 instead. To calculate the rest of our lower class limits, we just keep adding 10. So we start with the 670, add 10, so our next lower class limit is 680. Our next lower class limit after that would be 690, and then 700, 710, 720, and 730. So here are all of our lower class limits. Now we need to find the upper class limits. And again, we're going to look at the lowest class limit of the next class. So for this first one, we're going to look at the 680, and we want to make this 1 unit less than that. So our upper class limit for our first class is going to be 679. And the reason that we make it 1 unit less is that we can't have our classes overlapping. Each data value has to fit into one and only one class. So we can't make this 680, because then if we had a data value that was 680, we wouldn't know which class to put it in. Now our next upper class limit is going to be 690 minus 1, so that would give us 689. And another way to calculate this is, just like we did with our lower class limits, once you have this first upper class limit, you can just start adding the class width on. So if we took 679 plus 10, we'd get 689. And then we can just go down through the rest of our upper class limits. And notice this last one, the 739, we don't have a next lower class limit to look at, so we just add 10 to the previous upper class limit. Okay, once we have all of our classes determined, so here are all of them, then we can go through our data and find the frequency for each class, just like we did with qualitative data. So this is our frequency distribution. Now sometimes we have discrete data and relatively few different values, and in that case we may just make the classes the different values of the data. So this frequency distribution here represents the number of available cars in a household based on a random sample of 50 households. And these were all of the values that were in the data. It just went from 0 up to 5. So it's easier just to make those values our classes. So here we're just going through and counting how many zeros there were, how many ones there were, and so on. And a histogram is an important type of graph that portrays the nature of the distribution. A histogram is similar to a bar graph, only it's used to represent quantitative data instead of qualitative data. It's going to look a lot like a bar graph though. We're going to use the classes that we came up with for our frequency distribution, and we draw a rectangle for each class. The height of each rectangle is the frequency or the relative frequency of that class. And here's one difference between histograms and bar graphs. The width of each rectangle is the same, just like for a bar graph, but in a histogram the rectangles touch each other. Here's an example of a frequency histogram. We have data about the number of cars per household. We already had our frequency and relative frequency distributions for that. And if we want to do a histogram, notice here we have our different classes going along the horizontal axis and our relative frequencies on the vertical axis. And notice again, our rectangles here touch each other instead of being separated like they were for a bar graph. And a stem and leaf plot uses the digits to the left to form the stem and the rightmost digits to form a leaf. For example, if we had a data value of 147, usually we would use 14 as the stem and 7 as the leaf. The leaves are listed in order from least to greatest. And some statistical software, if we have it create a stem and leaf plot for us, actually gives us the frequencies for each stem. So this can be an easy way to get a frequency distribution. So here's an example of a stem and leaf plot. Here are the stems over here, and in this case it told you that the stem represents tens and the leaves represent units. So the values here, if our stem is 5, that means that's 50 and our leaf is 0. So that data value would be 50 and this data value would be 54. The data value represented by this leaf would be 80 because the stem was 8. Sometimes we have so many data values that we want to separate them a little bit, so we can use split stems. So this stem and leaf plot is just taking the one up here and breaking each stem into 2 pieces. So each one, this one goes from 0 to 4, and the second one will go from 5 up to 9. So this is just taking the data up here and splitting it into 2 parts. So here's the 2 parts for the 2 stem, 2 parts for the 3 stem, and so on. Dot plot has each observation on the horizontal axis in increasing order, and we just place a dot above the observation for each time it's observed. Here's an example of a dot plot. We're back to our data about the number of cars in a household. So here's our dot plot, and again, this is just a frequency distribution represented with dots instead of numbers. So for the 0 class, we have 4 dots. For the 1 class, we have however many dots that is. And again, this gives us an easy way to look at our distribution. It's a lot like a histogram, only it uses the dots, only it uses the lines of dots instead of the rectangles. Different distribution shapes. The first one is a uniform distribution, and in this one the frequency of each value of the variable is evenly spread out across the values of the variable. In other words, the frequency for each different value is the same. If we have a bell-shaped distribution, that means that the highest frequency occurs in the middle of the graph and the frequencies tail off to the left and to the right. And for a bell-shaped distribution, we want it to be approximately symmetric. So if we look at the very middle, where the highest frequency is, we want to have a mirror image on each side of that. Now if our distribution is skewed right, that means that we have a long tail on the right and the bulk of the data on the left side of the graph. And this gets a little confusing. You have to remember that a long tail on the right means it's skewed right. So skewed left means that we have a long tail on the left and the bulk of the data on the right side. Here are 4 histograms. This one has a uniform distribution. Again, every frequency is the same for each class. This one is bell-shaped. Again, we have the highest point in the middle, and it's approximately symmetric on each side. And notice that we have a tail on the left and a tail on the right. This one down here is skewed right, again because we have a long tail on the right and most of the data is on the left side. This one is skewed left because we have a longer tail on the left and the bulk of the data is more towards the right of the graph.